Hello viewers, welcome back to another section of my YouTube channel tutorial. In our previous video we talked about differential equation, the order, linearity, and in this video we are going to continue with the different types of differential equation as well as how you can tackle them. So we are going to consider first order linear differential equation in this tutorial. First order linear differential equation. So first, I told you we have first order, second order, third order in the previous video. So you know what order is, and linearity, what a linear differential equation is. So let's move straight to what we have in this video. Linear differential equation, which is the first order, is always in this form: dy over dt plus p of t multiplying y is equal to g of t. I'm going to break this general equation down. The dy over dt is our derivative. P of t is a constant or a function multiplying the y itself, which is not in the derivative form, and is equal to g of t, which is any other constant or non-constant functions. So when they give you any equation and you are able to express it in this form, we will say that it is first order linear differential equation. We have an approach to how you can solve first order linear differential equation to get our y. As I told you earlier, differential equation is about finding y or finding the derivative in it. You want to reverse it. So how do we find the derivative? To find antiderivative is simply taking integral, but since it is an equation, it wouldn't be that easy. So you need some techniques, and that is what I'm going to show you in this video. Kindly watch this video to the end. Don't forget to like, to share, and if this is the first time you are seeing this channel, kindly subscribe to support. So, as I've explained the general form, to solve every first order linear differential equation, you need what we call the integrating factor. The integrating factor. So integrating factor is what is going to help us solve first order differential equation. So it's simply integrating, then you add a factor to it. So integrating factor. So the integrating factor in this equation and in this video, we are going to represent it with mu of t. So mu of t, that will be the general representation of our integrating factor, mu of t. So now let's see what the integrating factor is and how you can find the integrating factor. So integrating factor mu of t is generally equal to e to the power integral of p of t multiplying dt, then plus the constant k, but that constant has been solved in the derivation of this formula, so let's end here. So always integrating factor is equal to e to the power integral of p of t dt. What is p of t? P of t is the coefficient of y. So if you have dy over dt, then plus p of ty. So when you express your equation in this standard form, the coefficient of the y, which is not the derivative form of our dependent variable, is what we find the integral and to the power of the e. So now let's see how we can apply what we've learned now to solve a simple differential equation. So let's see a differential equation. Let's say dv over dt is equal to 9.8 minus 0.196v. So let's see. This is a simple differential equation. dv on dt is equal to 9.8 minus 0.196v. How do you know that it is linear and it is first order? It's first order because dv over dt here is only first derivative. It's not the squared v, it's dv over dt. And also there is no square here, and meaning it is linear. Now you can see that the dependent variable dv here has its corresponding v here, and meaning that's going to be linear. And for linear, we found out that the general formula is what? The y on the t plus p of ty equals g of t. So always the coefficient of our derivative should be 1. Take note. Then you make sure that any term containing y or containing our dependent variable here should be on the left side. So in our case it's v. So whatever containing v should come to this side. And that is the most important thing to express it into the standard form. So now we have to move the 0.196vt to the left side. Then we find the rest. So to express this, I'm going to have dv on the t. So dv on dt plus 0.196 0.196v, then it will be equal to what I have on the right side. The rest will be on the right side, 9.8. So you realize that this expressed into the standard form, only terms containing the v or containing the dependent variable should be on the left, and any other term should be on the right. Once you reach here, the next thing to do is to find our integrating factor. Mu of t is equal to e to the power integral of p of t dt. So our integrating factor mu of t is equal to e to the power integral. Now the p of t is the coefficient of the v, that is 0.196. 0.196. Then we bring our hot dt because it's mu of t, and this is our integrating factor. So we have to solve this to get our integrating factor. Now what is the integral of this? From calculus, you are going to apply calculus here. So let's see. At this point, to find the integrating factor mu of t, I'm going to get here, when you integrate this with respect to t, a t will be added, right? So I'll get my integrating factor mu of t will be equal to e to the power 0.196t plus a constant, but the constant is omitted in the integrating factor. Whenever you are doing integrating factor, after integration, we don't add a constant k to it. Take note. So at this point that you've got our integrating factor, what are you going to use this for? Now we get back to our equation. We are going to multiply the integrating factor by every term in our equation. So you get the v on the t times the integrating factor e to the power 0.196t plus the 0.196 I have here 196v multiplying e to the power 0.196c. Then it will be equal to 9.8 times 9.8. So we are multiplying through the equation times e to the power 0.1960. So at this point, let's derive something here. The v on the t is a derivative of v, so let's say v prime. This is our integrating factor, right? Then 0.196v e to the power 0.196. You realize that this v that we have here is actually the undifferentiated form of what? The v on the t. So we have differentiated form for v here, the v here, it wasn't differentiated. Here our integrating factor was as it is here, but I realize that when you differentiate this 0.196t e to the power this, you are going to get 0.196 multiplying e to the power 0.196t, meaning that here our integrating factor is differentiated. So see, here we have our u not differentiated, then plus here we have our v not differentiated, but we have our integrating factor differentiated. That is our integrating factor prime. So from here you can see that it is product rule of what? The integrating factor as well as what? Our v. So it's actually v multiplying mu of t all to the power what? Prime. So if you have this, it can be expressed into this. Therefore, whenever you reach this point, it is assumed that the integrating factor times the v or times the undifferentiated form of our derivative will be a product, and all will be to the power a derivative. So that is the simplification we use here. It's, that is the proof of the assumption here. So now from this point we move straight to v multiplying the different the integrating factor. So see it all here. So you have our v here, and it will multiply the integrating factor e to the power 0.196t, and all this will raise to the power prime from our rule derived here. So this will be equal to what you have on the right side, 9.8 multiplying e to the power 0.196 1960. And at this point, we want to find v. That is the goal of our operation here. We want to find out v. So how do we find v? We find v by making sure that it stands alone. We have a derivative. To remove the derivative, we take integral on both sides in order to remove the derivative. So we take integral on both sides to remove our derivative so that we can find our v as the solution. So this should be equal to the integral. So when you are taking integral, we take on both sides so that it's going to be accurate, because whenever you have equation, what you do to the left side, we do to the right side. E to the power 0.1960. So at this point, we can clearly see that our derivative is going to cancel the integral sign here, because if you integrate a derivative, it cancels out. So here we'll be left with v multiplying e to the power 0.1960, right? Then on this side, that is where we do the actual integration. So this should be equal to, when I integrate, so see, whenever you have this, you have to perform this simple integration. So you are going to have 9.8 being a constant out. So 9.8 out. Then when you integrate this, you realize that this is a composite function. So you let u, so that is has been treated in the calculus you've done. So I believe you can simply integrate this part. So you get this dividing the whole thing back again. So you get this over 0.196, then the e to the power 0.1960, then plus our constant of our integration. So at this point, we have been able to integrate this side, but our goal is to make v the subject. So now let's simplify this further. So let's see. At this point, I'm going to have my v e to the power 0.1960 is equal to, this simple evaluation here gives 50 e to the power 0.196t plus k. So when you get to this point, the next thing to do is to divide through by the coefficient of our v, because you want to find v standing there alone. So you divide through. So here, when I divide through by e to the power 0.196, I'm expecting it to cancel out. so that it will cancel this out. Then here to e to the power 0.196 c. It will also cancel this out because I have that thing here. It will cancel this also out. So if you have like thing here, it's going to be cancelled out. But here you divide it by e to the power 0.196 c. So at this point, my v finally becomes 50 plus k e to the power negative 0.196 c, because this one will move up. And this is a solution for a differential equation. We have been able to make v the subject. So differential equation simply means that you are reversing the the derivative in your equation to make the dependent variable stand alone. Thank you for joining me to this time. This is the end of our first order linear differential equation. See me in the next video for separable differential equation, and you enjoy the class. Thank you.